Okay, so last time we saw the little introduction to volumes, right? And we basically, we saw how a solid is created, right, by revolving something around the x-axis in order for us to be able to find the volume of it. All right, so the way we talk about the volume of a solid is it's the integrable cross-section so if we have so what we do is we take the area, right, of a solid, the cross-section of the area, and then when we find the area of the cross-section from A to B, we then add up all of those areas. So what we do in order to find the volume is, so suppose you have, a function f of x, and then suppose you have a function g of x, and let me make g of x look different here, okay? If I take, so if this is a solid, like a three-dimensional solid, and if I slice it, and if I look at, a cross-sectional area, and then if I integrate over all the areas from A to B, that's how I find volume. Okay, so let's talk about how we're going to do this for our purposes. How do you find the volume? By slicing, right? So first, what you want to do is sketch a typical cross-section. All right, so what is a cross-section? If you take any object and if you slice it and, cut it open, and now if you look head-on at the surface where the knife, like went through, right? That's a cross-section, right? So if you take, like, a cell phone, like if you have it, lying down like this, and if you, vertically slice it, and then if you look head on at the region where the blade cut, what shape is it? It's a rectangle, right? So that's the cross-section. So what we do here first is you are going to draw a typical cross-section. So in that case, it was a rectangle. So it could be a rectangle, it could be a triangle, right? Square, circle, semicircle, and so on. Next, you have to find a formula for the area of AX, and normally this will involve y, your function, okay? Now, if the cross-section is perpendicular to the x-axis, right? So if it's perpendicular to the x-axis, the cross-section length is the upper curve minus the lower curve, okay? So that's the length. Remember, like we do, like just like when we were doing area, upper curve minus the lower curve. If the cross-section is perpendicular to the y-axis, right? If the cross-section is perpendicular to the y-axis, then we have to do the right curve minus the left curve. All right, that's how we find the formula for A of x. Then we have to look at the limits of integration and then integrate A of x to find the volume, right? So remember, when we integrate, that's like adding infinite pieces. Okay? And so if I have infinite disks, right? And if I add up A times dx, area times the length, that's the volume, right? And then if I integrate over the whole region, then I'm adding up all of the tiny little itty bitty volumes, and then I get the volume of the shape.
The dx is
The dx is the height. Yeah, it's the width. Okay, it's the depth.
Yeah.
Okay.
Like this way.
So take a look at this. A solid lies between planes perpendicular to the x-axis from x equals 0 to x equals 4. So take a look at what happens here. You know, the x and y-axis, right? Well, we took the x and y axes, and now we inverted it, so now it's lying on the floor, right? So now we're getting, you see that? Like now it's lying on the floor. Okay, now the cross sections are squares with bases in the xy plane. And they are perpendicular to the x-axis between these, sorry, let me read that. The cross sections, which are squares with bases in the xy plane, are perpendicular to the x-axis, and they run from y equals negative x to y equals positive root x. Okay? Find the formula for the area of one of the cross sections, and then use it to find the volume of the solid. Okay, so take a look here. I have my solid. So take this. Imagine like I revolve this around the x-axis. Do you see how it's gonna look like a bowl, yeah, right? Like this, okay? Right? It's gonna be like a complete solid, but it's gonna be like a bowl, like this, okay? Like a three-dimensional, sort of like a bowl. This is how it's gonna look, but now it's lying on its side, okay? When I revolve it like this, it's gonna look like sort of like an acorn-ish, okay? But it's a solid completely. Now, this is such that when I slice it, the cross sections are squares, okay? Now, do you see how the square here is small, but the square here is much larger? Do you see that? So they've drawn those squares up here for us. So the cross sections are squares. What we're going to do now is we're going to find the area of every single one of these squares, multiply it by the little thickness, right? That gives me the volume of one of those tiny square discs. And then when I add them all up, all of the volumes, then I get the volume of the entire shape. Yeah.
Wait, so how is it a square if, like, when you revolve it, look like an acorn? Like, how is it? Like, wouldn't it be a circle then?
The way in which you cut it is a square.
Is it always going to be a square?
Yeah. Okay. It will tell you basically how you do it. Remember how? Okay. You remember how when we did area under a curve?
You can make it all
Okay. Do you remember how we did, like, when we did area under a curve, right? We could do rectangles underneath.
Oh, but it's just not the whole thing.
Yeah, or we said we could do trapezoids, right? So it's similar to this. You could draw any shape inside that you want, right? Yeah, so these squares, they're not going to fit, like, snug. There are going to be, like, some empty spaces, but this is just, you know, one way of doing it, yeah.
If you refer to like, the little thickness, like, this is how you find out that like measurement.
You don't find the measurement. It's dx. When you do the dx, it does it for you. Okay. Yeah, okay? All right. So first, let's find the area of this, right? So first step is draw a typical cross section. So we're going to draw a cross section. This is one of the cross sections, right? Now this is a square. That means the sides are equal to each other, right? Okay, now if this is the square, right, look at this. This is y equals root x. And then this is y equals negative root x. Is that right? So now, the distance from here to here is y. So that's root x. That distance is root x. Okay? So that means this yellow is, green is how much? That's 2 root x. Where is that green here? It's that much. That's 2 root x. Okay? So it's like I have taken this square here with the green side, and now I've transported it here.
So we're taking the max on them?
Any one of them. It doesn't matter because it's 2 root x. Whatever x is, it's 2 root x. Yeah. So if that side is 2 root x, then this side is also 2 root x. So the area here is equal to 2 root x squared. So the area is 4x. Okay? All right. Now, what's the volume then? Right. The volume is the integral 4x dx. And now, this is going from x equals 0 to x equals 4. And that's how we integrate. Okay? Now, most of the time, you're not going to be given that cute little square diagram on top. Most of the time, all you will be given is this. Okay? And so from that, how do you figure all this out? Well, you're being told that there's a solid, right, from x equals 0 to x equals 4. The cross sections, which are squares with bases in the xy plane, right, are perpendicular to this x-axis, and they run from root x to negative root x. So how do I translate that? If you have to imagine a square, right? The cross section, so the solid is coming out of the board, out of the page like this. And the cross sections, when you cut them, are squares with bases in the xy plane perpendicular to the plane. So this is how that looks. Okay? Perpendicular to the plane, going into the plane. Orthogonal. This is where orthogonal comes from. So perpendicular to the plane. So I have square after square after square. And now, if there is a square coming out of this page here, then the green that I drew over there represents, that right there. Okay? And now, so that's the side of one of the squares, which is a cross section to this. How much is that green side? Well, it's root x and another root x, 2 root x. Now, what's another? Okay, so conceptually, yes, it's a length of root x, a length of root x. What's another way that I can get root x, 2 root x? Well, it's the upper minus the lower. And if I do upper minus lower, then I have root x minus negative root x, 2 root x. Do you see that? So every which way you look at it, that's what we're doing. It is important that you know how to do it conceptually. It is important that you later do it automatically as well. But you can only start doing it automatically when you understand conceptually what's happening. Okay? All right? So we're going to do more later with the same example. So when I integrate this, it's going to be 2x squared from 0 to 4. And that turns out to a volume of 32. Okay. Okay, now, if there are not any units given to you, then there are no units. Yeah.
Well, we get in the questions where we train it.
When you do what?
Where it's just rotated around that axis and then it's the area of like circles.
Yeah. We're gonna do like we're only at 1% of this lesson. Okay. Now it says use the same base as example 1 and use cross section that are semicircles with diameters in the xy plane and perpendicular to the x-axis. Okay, so I have y-axis, x-axis, root x, negative root x, from 0 to 4. Now, I have semicircles.
So is that length and height or radius?
Nothing. Hang on. Now I have semicircles. Now the cross sections are semicircles with diameters in the xy plane. So semicircles with diameters in the xy plane perpendicular to the x-axis. Like this. Okay? So now a diameter then is this. This is one of the diameters. So first we said draw a cross section. That's a semicircle. The diameter, which is that red line, is this. Right. So that is 2 root x, right? Which means the radius is 1 root x. So now, the area then, remember its area as a function of x, it's a semicircle, so it's half of pi r squared. So a of x is pi over 2 x. Okay, well, how do we find volume then? It's the integral of pi over 2 x dx from 0 to 4. And of course, we don't have to put the pi over 2 in there, right? We can easily have said pi over 2 from 0 to 4 x dx. So this is pi over 2 x squared over 2 from 0 to 4, and that's 4 pi. Now, that's a different volume. That's because, as Hannah was pointing out, when you cut this, they're not really squares. The cross sections are not squares. What we were doing is we were piling up tiny little squares in this, but in doing that, there was a lot of space that was left out. Now, a semicircle, right, because of the curvature of, like, the curved nature of it, might be a better representation of the volume or the surface, the contour, just like a trapezoid was a better representation than rectangles were, okay, for area. Okay. All right, let's do one more. A solid lies between planes perpendicular to the x-axis from x equals negative 2 to 2. The cross sections, which are isosceles right triangles with bases in the xy plane, are perpendicular to the x-axis, and they run from y equals the square root of 4 minus x squared to y equals 0. At this point, when you see the square root of 4 minus x squared, you should know that that's a semicircle, okay, to y equals 0. So, let's draw this thing. That's what it looks like. So we go from negative 2 to 2, and then y equals 0 here. The cross sections are isosceles right triangles. Okay?
Isosceles is two.
Yep. Okay. Isosceles right triangle with bases in the xy plane. Sometimes the hypotenuse will be in the xy plane. But now the base, one of the bases, is in the xy plane. It doesn't matter which base because they're identical. All right? So notice I always like highlight this and I then highlight that so I know. So now that red line in the graph here, right, is y, okay, which is right, the square root of 4 minus x squared, minus 0. But that's just the square root of 4 minus x squared. If it goes from the x-axis to the graph, it's the length of y. So this is 4 minus x squared, and so is this. So the area of the cross section then is half base times height, so it's the square root squared. So a of x is 2 minus half x squared. Okay. Volume is the integral from negative 2 to 2, 2 minus x squared over 2 dx. Okay, now take a look here. Do you recognize how the integral here is twice, like it's symmetric, so it's twice the integral from 0 to 2? So I'm gonna take advantage of that. So I'm gonna do 2 times 0 to 2, 2 minus x squared over 2 dx. Why do I do that? Because later on when my lower bound is 0, that's easier to plug in than negative 2 is, right? So this is going to be 2 times 2x minus x cubed over 6 from 0 to 2. So that's 2 times 4 minus 8 over 6, which is 4 over 3. And that's 16 over 3. Hey. Okay, so we did a couple of different cross sections, right? We did a cross section which was a circle, a square. We did one which was a semicircle, and then we did another one which was a triangle. They could be any shape, honestly. But now, the most accurate is definitely when we take circles as cross sections. Okay? Yeah. Because then you just have like, because when you rotate you get like this rounded outside, and so when you have like, you know, tiny little discs, it's a lot more accurate. So the formula for area is going to change somewhat, right? These solids now are going to be called solids of revolution, right? So let's take a look here. Look at this shape here, right? This is f of x. And if I rotate this around the x-axis, then the shape that I get is this, right? It looks like a vase. Now, imagine I draw a series of discs in here, okay? So this is the circular disc that I have drawn in here. Do you see, to find the area of this disc, right, it's pi r squared, correct? And the radius is always going to be f of x. Do you see that? So the area then is always going to be, always going to be pi f of x squared. Right? Why is that? This is because area is pi r squared, and r is f of x.
Okay.
Right? So then, in order to integrate and find the volume, it's always going to be, right? Volume is always going to be the integral of pi f of x squared. But I can always take the pi out, right? Because it's a constant. So it'll be pi integral f of x squared dx. Every single time. Pi f of x squared dx. Okay? And one way we write that is this. Pi capital R squared dx, and then R is just f of x, right? It's just that region, sort of. Okay, so let's do one. The line between the graph of f of x equals 2 plus x cosine x, that's what that is, and the x-axis over the interval -2 to 2, so that gray region, is revolved around the x-axis to generate a solid. Find the volume of the solid using a calculator. Okay? So these will either be on a calculator section and so on. And before you reach for your calculator, let's first write the volume here. We're going to do it using circular discs. So the volume is going to be pi integral of r squared dx. R is f of x squared dx. Please, 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 please remember from where these things came. This is a circle. A circle has an area of pi r squared. The radius is the length of the y, right? So pi r squared. Pi r squared. And of course, we're going to go from -2 to 2. Okay, common issues, problems, mistakes. People will forget the pi in the formula, and then, or you put it here, and then when you put it in your calculator, you forget to put the pi. All right? So once you put this in the calculator, the volume is 52.4288.
Solve that integral without a calculator?
No, not yet. We don't know how to integrate x cosine x. That is in BC. That's a different. That's not use substitution. That's not use substitution. That's integration by parts. BC. It used to be in AB, and I used to cover it all the time. They took it out. Yeah, I used to teach it all the time. That was one of my favorite things to teach. Okay. Now, when you have, remember last time in the video, I showed you, the situation where you have a curve and then another curve, and it's this that you're revolving around the x-axis, and so then, when you revolve like this, this is what the solid looks like, and there is like empty space in the middle. Do you remember that? Huh? Yeah, it does look like an Amitashin. Right? Okay? You guys remember that? So now when I draw a cross section, I get a rasher and not a disc. And so what the cross section looks like is this. And now if I want to find the area of the shaded part, this is back from, when we were in middle school, pi big R squared minus pi little r squared, right? The big area minus the little area. Well, that is just pi r squared minus r squared. Factor out the pi. So when I need to find the volume of it, it's pi capital R squared minus little r squared dx. And so r is the outside or the larger function, and little r is the inside function.
This is when there's two different.
This is when there are two different functions.
The other ones
were to the x-axis, correct. So here, this is where you're going to be doing farthest from the axis and in. So either the upper minus lower or right minus left. Okay? It all seems so simple now. Okay, so, oh, I have that here. So capital R is the curve farthest away from the axis. Little r is the curve closest to the x-axis. Okay. Okay, look at this one. The region in the first quadrant enclosed by the y-axis and the graphs of cosine x and sine x is revolved around the x-axis to form a solid. There are two curves here, upper and lower. Which is the cosine, which is the sine?
Cosine is top.
Cosine is upper because it starts at y equals 1. So y equals cosine x and y equals sine x. This entire gray region is now being rotated around the x-axis. So imagine it being rotated, right? Imagine just this gray part being rotated like this. What it looks like is the one on the right, right? So the solid part is this stuff, okay? And then inside of this funnel shape is empty space, okay? So now, when I take a cross section and I look at it, it looks like that pink or purple, whatever it is, it's a washer with a hole in the middle. Okay. So, because y equals cosine x is farthest from the axis around which we're revolving, that is big R. Because sine x is the closest to the axis over which we're rotating, that's little r. The volume, okay, is pi cosine x. Okay, remember, this is the important part. This is what some students miss. It's not r minus r squared. It's cosine of x squared minus sine of x squared x. Now, about the intersection point. This is a no calculator problem when it's cosine and sine. About the intersection point. We want the point where cosine x is equal to sine x. And we know, right, that in those triangles, cosine and sine have the same value at x equals, or at pi over 4, right? And the value is what? Cosine of pi over 4 and sine of pi over 4 are root 2 over 2. So that coordinate point is pi over 4 comma root 2 over 2. This is a no calculator problem. Okay. So now, this is going to go from 0 to pi over 4. No. Huh?
The bottom part, it says from negative pi over 4 to pi over 2 by negative 1.5. 1.5. What is that?
That's just the window. That's just this window.
But we still have to figure out the bounds ourselves.
Yeah.
By figuring out where the two equations are
Yeah.
equal to each other.
Okay. So when you integrate all this, we get pi over 2. Yeah. Okay. Oh my, let's continue. Okay. Find the volume of a solid generator revolving the region bounded by the lines and the curves around the x-axis. So I have y equals 2x, right? So y equals 2x, that looks like this. And then, so at -1, it's -2, like this. You're welcome. So that's y equals 2x. And then I have y equals x, looks like this. And then I have x equals 1. Looks like that. So the area that I want is this one. Okay? So that's what I'm going to be rotating here. Okay, so look at that region. Imagine there are disks here, right? So disks like this. In each case, right, their washer. The radii, right, it's a vertical radius here. Upper is the purple, lower is the blue each time, right? So capital R is 2x, lowercase r is x, and so when I take the volume, it's going to be pi times 2x quantity squared minus x squared dx from 0 on. And so this is going to be pi 4 over 3x cubed minus x cubed over 3 from 0 to 1. That all goes to 1, so it's just pi. Okay, let's do this one.
I just don't like how she has this
So, example 7. Yep, me too. Okay. So the region bounded by root x and half x. The region of so this is the region, and we're gonna rotate it around the x-axis. So again, you have two functions. It's like a sliver, meaning it's gonna be capital R minus lowercase r. So capital R is the upper one, root x. Lowercase one is the smaller one, half x.
Because they're gonna turn out to be circles. Is there a hole?
Yeah. Okay. Yeah, there's going to be a hole in the middle. It's going to be a washer. So, okay, so the way it looks, right, if you have a disc or a washer in there, so you have one disc that looks like this. So look, if you rotate this, it looks like this and this. Okay? And so you have one that looks like this, and then another one inside looks like this. And the region that you're integrating is the one in between here. Yeah, it is. It actually is. Okay, so you see how the radius here, the shaded radius, is capital R minus little r. Okay? So, now, we need to know, however, what this is, right? What point this is. The intersection, the point of intersection is, you set root x equal to half x, so you set the two functions equal to each other. When you square, x is 1 over 4x squared. Okay? So, well, no, so it's going to be like 4x equals x squared. So x squared minus 4x equal to 0. Now we take out an x. So this happens at x equals 0 and x equals 4. And sure enough, x equals 0 and x equals 4 is where they meet. Now, the y-coordinate, what you do is you take each of these points and you plug it back into one of the functions. So this is 0, 0, and this is 4, comma 2. Okay, the volume is going to be pi root x squared minus half x squared dx from 0 to 4.
Contribute like the first thing, simplify before you say area equals simplified 4 and then the volume equals 4.
I mean, minimize the work. Whatever is easier for you. Okay. All right. Now we're going to revolve around the y-axis. Same graphs, but now we're revolving around the y-axis. So now we're going this way. When you do that, what it looks like is I have one here and another one here. Right? That's what it's going to look like. It's going to be like a funnel. And so now when I draw the discs, I have one disc like this and another disc in the middle like this, right? And so the area, the shaded area is this outside. Okay. Now, when I'm revolving on the y-axis, it has to look different, right? It has to be with respect to y. So I have to change everything with respect to y. So if this one was this one was y equals root x, then this is x equals y squared. And the bottom one, if it was y equals half x, it's now x equals 2y. So capital R is now the one farthest from the y-axis, which is 2y. Lowercase 1 is y squared. So volume is pi. Now it's 0 to 2, right? Because this one, right, was 4, comma 2, so I have to take that 2. 2y quantity squared minus y squared squared dy. And when we integrate, whether calculator or not, it's 64 over 15 pi. And it's perfectly acceptable to leave your answers in terms of pi. Because it's pi r squared minus pi r squared. Yep.
I like the ones with these where you have to like split it up like we did for the last one.
Not really. Not really. But there are going to be ones where you don't revolve around the x-axis, you revolve around some other random line.
Wow.
I know. That, yeah. That's, I think I'll do that tomorrow. Okay? So, as far as the homework is concerned, you can do all of them except, I believe, number 21. Right? So you can skip number 21 and you can do the rest. Okay? Yeah. I mean, it's only 21 and followed by 25 anyway, so you just do 21 and 25 out of order. So, for homework, do the book problems except 25, right? And I actually do want you guys to, except 21. And I actually do want you guys to start now.